Welcome to week 4 of the course. Very important week. We're going to talk about regression, and we'll also talk about regression trees, which is a technique from machine learning. So let me start. Regression is maybe the most widely used statistical tool. Remember, we're going to have input-output pairs, x's and y's, and we'd like to predict an outcome of interest. That's our y variable from our initial x variables. And typically we'll have a high dimensional x variable, and we want to try and figure out how to predict y. And we're going to come up with a model or an equation that connects the response or dependent variable, that's the y, with the predictive variables, as we said, x. Okay. The chapter, if you're following along in the AIQ book, the chapter is the Henrietta Leavitt chapter. She was an astronomer, and back in 1912, she used a regression technique on her pulsating stars data set, and she also used some image recognition, deep learning type tools to understand what was going on. So I refer you to the Henrietta Leavitt chapter. Okay, so one thing that's discussed in AIQ is how do you fit a regression model or a regression line to a set of data. So on the left-hand side, we see we're going to have the optimum fit, and we're going to measure by mean squared error in this example here. And if we use a line here where the slope isn't quite correct, we see that we get a larger error. And by error, we mean looking at all the residuals from the line and squaring and averaging them. And you can see that for linear regression, we'll find a solution to find out, well, what's the optimum regression slope beta hat for that line. And essentially, Henrietta Leavitt used Gauss's principle of least squares, and that's something that we'll see later on today. And the idea is to find a prediction rule. So if I give you a new value of x, say x equals 25, I'm going to go up to the line, and I'm going to then go over and make my prediction for what I think that y value should be. So the whole idea is, given an input x, can I come up with a prediction rule y hat at that level of x? Okay, so there's many questions related to prediction. We'll spend a little bit of time talking about Zillow on the next few slides. So something called the Z estimate. How much will my house sell for? Will the Chicago Cubs win the World Series? Will a person like a movie? Related to the Netflix prize, which was one of the first machine learning competitions that was run online. A website, Kaggle, which is now owned by Google, has a whole bunch of data sets that people put out with leadership boards, and people publish their methods and algorithms for finding good out-of-sample predictive mean squared error. Okay, so many prediction problems. As we go through the next few weeks of the course, you'll see me talk about models, parameters, and estimates. There'll be one random variable y of interest. As I said, a bunch of explanatory variables or characteristics x. That will entail in estimating parameters. So for example, in a linear regression model, we need to estimate the intercept and the slope. There'll be a slope or marginal effect for each of the x variables in my data set. And the whole goal of of building a model is to understand that relationship between y and its input variables, and then to help us make better predictions, better decisions, and evaluate risk, etc. Okay, so let's start at thinking about predicting house prices, and the machine learning company that has done an incredibly good job of this is Zillow. It has an incredible database of well over 100 million houses with a time series of sales that have been provided. And the whole idea is to look at property sales data and a whole bunch of characteristics on a house. So you could imagine a huge big data set with characteristics such as location, age, number of bathrooms, square footage, location, for example, waterfront or not waterfront. And the whole idea of Zillow is to build something called a Z estimate. And when Zillow first started back in 2006, the Z estimate model had about a 14% error rate. Now it's down to just over about 1%. So, and again, the other interesting thing, Zillow's moved into looking at rental prices. It's also moving into, it believes so much in its Z estimate model, it's willing to offer people offers for their houses so it can buy and then resell. And you can imagine a whole bunch of characteristics, and you can imagine with an incredibly big data set and with clever statistical tools, you can actually assess what's the marginal value for each part of the house. And again, none of these things are perfect, and over time these things are improving. So still a lot of effort gets put into managing that incredibly big data set, providing maps of previous sale prices, characteristics of houses, and trying to improve the Z estimates. Okay. Again, if you go through these hyperlinks, you have a whole bunch of links to read. As I said, Kaggle is a website that provides data sets with prizes if you can outperform previous models. And as I said on the previous slide, in 2021, this is down more to the 1% range. So there's lots of possible characteristics that you can add for predicting house prices: size, zip code, location, parking, nearby schools, waterfront, etc., etc. Rental prices nearby, and many other things. Okay, so let's just do a very, very simple example. Let's just take one y and one x just to illustrate what would happen. How do I predict house price from size of the house? So first thing I would do is I would just plot the data and see if there's a linear regression straight line. And all R is doing is it's finding the optimum slope and intercept of that line. And so it's trying to tell you is that if I increase the size of my house by 1,000 square feet, how much will my house price go up? So I want to find that regression coefficient. If I think of it as a modeling problem, I've got an equation that writes the output variable price as an intercept, a slope times an input variable, and then an error term. And we'll assume that the error term is normal, mean zero, variance sigma squared. And again, just like in the basic statistics week, we'll be able to provide an estimate, a little s squared of our error variance, and we'll also be able to imply our diagnostics to see whether that assumption holds true. And so for every 1,000 square feet increase in price in this data set, it'd be 110,000 increase in the price. You can use your regression model. Once you've found your equation between y and x, you can just plug in a new value of x, any new value of x you want, and out will come a predicted price. So a new house with size 2,200 square feet would have a predicted price of 262,000. So the intercept plus the regression beta times the size of the house. And the command that's used to get that out of R is the predict.lm command. What does the R code look like? It looks like this. The key line is really this one here, where you build your regression model using the linear model command lm, run a regression of price on living area. And as I said before, R will calculate everything for you. If you want the coefficients of the model, use the coefficient command. If you want a list of everything, use the summary command. Okay, let me do a more complicated example that mimics a little bit what Zillow does. So I want to talk a little bit about a more advanced set of techniques called regression trees. And then I just want to go back and do the theory of the simple linear regression model. But I think once you've seen the regression trees, you'll see how powerful some of these techniques can be. So in the machine learning database, there's a very famous data set called the Boston housing data. It's got 14 X variables, and it's got N 506 observations on house prices. And you want to predict the median value of house prices. And there's a bunch of X variables to do that sitting in there. Let me just take one variable, the LSTAT variable, so the percentage of population with lower social economic income, and see if that has an effect. And so to fit a regression tree, so you want to think of a tree as finding cutoff points. And as you go down branches of the tree, eventually by the time I get to the bottom, I'll be getting a sequence of predictions for prices here. So mathematically or simply, it's just fitting a step function to the data. So rather than fitting a non-parametric curve, it'll cut up the cut points will correspond to the cut points it's found, and you'll fit a tree like this. So it's essentially cutting up the X space into regions, and then inside a region just fitting a constant model. And again, you can see sort of generalizations of trees where you could fit more than just a constant model at the end of the lease of the tree. You could fit something more complicated. Trees are very fast to fit and very flexible as well. We'll also talk a little bit about something called random forests and XGBoost. Okay, so there's our example of a regression tree, just to say in words what I just said. If X is less than C, you go left. If X is bigger than C, you go right. And at the bottom of the tree, I basically have my predictions. And in that simple 1y, 1x example, it looks like that. If I have two variables, my cut points can depend on different variables. I'm still cutting on one variable, but it can switch between variables. And if I think about what my prediction rule now looks like in x1, x2 space, essentially I've cut it up into rectangles. And inside a rectangle, I'll have a prediction. So that's what it looks like in 2 dimensions. And of course, you can imagine the generalization to multiple dimensions. And again, here's what a regression tree prediction service would look like. And again, one nice thing with trees that's actually quite hard to do in just simple regression is that it does a good job understanding the interaction between two variables, x1 and x2. So different non-linearities in different parts of the space, rather than just assuming an interaction term like x1 times x2. Let me talk about bagging, and that's related to random forests. I could take what's known as a bootstrap sample from my data. So with probability 1 upon n, randomly sample from the data set you have, and then fit a tree to each one of those new data sets. And then basically you'll have B trees, capital B trees that you've estimated for each of your bootstrap sample, and then for an overall prediction, just average over trees. If Y is categorical, it's a little bit more tricky to figure out how to make predictions. There's the voting method, and there's the averaging of probabilities method as well. So, and again, random forest is very simple to fit. It's like 2 lines of code in R, the RF command, and again, you can essentially bag over a bunch of trees quite simply. What would it look like in practice? If I do 10 trees, it jumps a little bit too much, so it's still a bit too noisy. If I do 1,000 trees or 5,000 trees, it doesn't really matter. So a 1,000 tree fit would look something like this, giving us a good predictor. And again, it's a little bit it fits the data a little bit more closely than just a simple step function. So rather than taking one tree, I've managed to average over 1,000 trees, and it gives me a little bit of finer detail when it comes to prediction, so I can get lower out of sample mean squared error. There's another idea, I won't talk much about it, called boosting. Ensemble methods are popular, meaning I'm averaging over a bunch of models. Essentially, you fit a tree, and then you look to see what's left over, and then you fit the residual, and you just sort of keep on going. And the final fit is really just a sum over many trees. So there's another, an XG boost or gradient boosting is like another version of boosting. And again, these ensemble methods have been shown empirically to do very well, particularly in some of these Kaggle competitions as well. So another set of methods to look at. So simple trees, random forests, and boosting. And what would boosting look like? There's a couple of parameters to play with in boosting. And again, very similar to random forests, but you get something a little bit more finer than just a pure step function, and you'd get a fit something looking like that last plot once you've optimized. Okay, so I hope that Boston housing data set gives you a good idea of how you can take simple regression and take it into regression trees, and how you can find quite complicated structure in high-dimensional data, where you cut your X space up into different regions and essentially fit little regressions inside each region. So tree modeling has become very powerful. Okay, well let's take a step backwards and just talk about our simple linear regression model, and talk about our underlying assumptions and diagnostics related to that. So here are our basic assumptions in our linear regression model. Y is equal to beta 0 plus beta 1x plus error. Our errors are assumed to be normal, mean 0, constant variance. What's known as heteroscedastic variance would be when the variance changes in time. Again, we're going to estimate sigma squared by s squared. And that the overriding feature is that we have a linear regression line. Okay, so there I've said what I just said on the last slide, and what we're really aiming for is to get our best estimates. Remember, beta 1 with a hat would be our estimator. We're trying to figure out what's the effect of x on y. And in the multiple regression model, we'll have many x's, and each x will have its own beta hat. So we'll be able to estimate the effect of one variable, holding all other variables constant, and see what happens. And then again, as we talked about in our simple housing example, we want to, what's the power of all of these statistical models? You might have a house that you haven't seen in the data set before, with a new future level of x, and you can just plug it into the regression model, and out will come a prediction of what you think that house should sell for. Just a couple of little definitional things. Fitted values and residuals. The fitted value is essentially the point on the line, and the residual is essentially how far do you miss the line. So yi with a hat are essentially fitted values. E sub I, or sometimes epsilon sub I hat, given by this first term, is essentially the residual. And you'll see in a second that we'll standardize these residuals, and that'll provide a diagnostic to see if our normality assumption of the errors holds true. So let me talk about standardized residuals. So essentially EI divided by their standard error. EI is a random variable because yi hat depends on beta 0 hat and beta 1 hat, so that's estimated with error. And so there's a formula that we can calculate, depends on the leverage of a point, and then we can standardize to get standardized, or sometimes called studentized residuals. And if our modeling assumptions are true, then these standardized residuals will have a normal distribution with mean 0 and variance 1. And another nice little point is that outliers will simply have large residuals. So remember that 95% of the time you expect the residuals to be bigger than 1.96, So for example, any residual that's order of magnitude 3 standard deviations away from your prediction line is going to be seen as a case for a pretty big outlier. And again, when you run a regression model, it's always a good idea to look at residual diagnostics, first of all, mainly to check assumptions. If your linearity assumption doesn't hold true, then it'll break down in this plot here, and you'll see me do a few of those in a minute. And then we can also find outlying points. Actually, another concept which we'll look at is called influential points, and that's essentially any points that really affect our fitted values yi hat, or really affect our estimates of beta hat. Residual standard error is essentially S. S is our estimator of sigma, and in a simple linear regression model, it looks like this: yi minus yi hat squared. Remember, I've estimated 2 parameters here, so I've lost 2 degrees of freedom. So I divide by n minus 2. And I always like to look at the residual standard error because lower S variables will mean tighter predictions. And so if you've got the correct, quote unquote, correct X variables in your regression, you'll have a good estimate of S, and the lower the S makes it easier to, your prediction intervals will be tighter. Okay, why is that? Well, let's think about prediction. The whole point of building regression models is, number one, to find the magnitude of effects, what exactly are the betas, and then number two, to make predictions for a given price level. And there's 2 types of forecasts that you could make. One is a prediction interval, and one is a confidence interval. And we've talked a little bit about this before. If you wanted to predict the average weekly sales over many weeks, essentially you're just doing a confidence interval for sales hat. If you want to do the sales forecast for a particular store or the next store in a particular week, there'd be an extra error term that would be added here. And that extra error term has an extra variance sigma squared, so your prediction interval, remember, will be bigger than your confidence interval. And generally, it's prediction intervals that you want. You want to get the correct representation of uncertainty. How do you do this in R? Essentially, it's the predict.lm command. You first of all set up a new data frame at the level of x's that you want to predict, and I could do multiple x's, and I can tell R whether I want a confidence interval or a prediction interval. Here's what would happen in the example here. You'd get the fitted values at your different levels of x's, for example, and then you'd get your lower bound and upper bound for your prediction intervals and confidence intervals. And just note that the prediction interval ones are bigger than the confidence interval ones. Okay, so let's actually step back and remember Henrietta Leavitt. Back in 1912, was looking at her astronomy data and was using Gauss's least squares principle to fit regression lines, regression models to her data. So what's the idea of least squares? And there are generalizations and modifications of least squares, but least squares is definitely the test of time has treated it very well. And the idea is, how do I optimally choose an intercept beta 0 and a slope beta 1? Well, let's think about drawing different lines through my data set. Each line will have a residual EI. Some will be positive, some will be negative. Actually, the solution to least squares will be such that the sum of the residuals is equal to 0. Now, some positive, some negative, so let's square them so they're all positive. Let's sum them up. And then let's try and find beta 0, beta 1 by an optimization problem of minimizing that sum of squared residuals. Now, that's got it'll be quite sensitive to outliers. So one of the downsides of least squares is sensitivity to outliers. And some people have replaced this by things like mean absolute deviation, more robust measures, where I minimize sum of the absolute value of the errors rather than the squaring. And of course, the squaring looks something like this. Another nice property of squaring is that I can take derivatives, put it equal to 0, and there's actually going to be an explicit solution. And so here's something that's actually very interesting. in regression, I can find a specific solution. A couple of things to remember. X bar, Y bar, the sample means lie perfectly on a regression line, and that's also true in multiple regression. And that sort of makes sense. If I'm at the average level of X variables characteristics, then I should maybe just predict the average Y or average price. And so that's basically the top equation. The second equation is a little bit more interesting. Remember, S sub Y and S sub X are sample standard deviations. So beta 1, which is the coefficient you want, the regression coefficient assessing the magnitude of X, is essentially the correlation, sample correlation, but scaled by the ratio of standard deviations, S sub Y over S sub X. So one thing to remember, an important thing to remember, is that beta 1 hat is typically not equal to R. So looking at that correlation table between variables, really, or the magnitudes of correlations, doesn't really tell you much at all. It's the beta hats that you really want. So for example, be very careful if my standard deviation of X is very small and my S sub Y is very big. Even if I have a very small correlation like 0.01, if I multiply up, I can easily have a significant and economically large slope coefficient. And vice versa, I could have a very high correlation, 0.99, but if my S sub Y is small and my S sub Y is really big, then my beta 0 will be close to 0, and I can easily have an insignificant variable effect. So looking at correlation is a mistake. Looking at betas is what you really want to do. Oh, and there's a general formula. So let's if I have a big vector of parameters, the general formula will look like where X is what's known as my design matrix, my stacks X variables. There's a general formula for beta hat: X transpose X inverse, X transpose Y. So these formulas generalize nicely to multiple regression. Another way of thinking of beta hat in the finance literature, in factor modeling, they'll think of beta hat as the covariance of X and Y, or Y and X divided by the variance of X. Again, just so you realize, the red line is our optimum line. So we've minimized least squares. That's our optimum line. But there's still variability in the slope. So there'll still be a variance of beta 1 hat, or even a standard deviation of beta 1 hat if I take the square root. And that's seen by all the green lines, which are not terrible lines, but possible lines that could go through my data. So, and you can see that the variability is going to be tighter in the center of the data. And you'll see that in the prediction bands too, that when you try and do prediction, the bands will be smallest at the origin and widest as you come to the extremes. A couple of facts. So R has coded up and calculated all these standard deviations for you. So there's a formula for the standard deviation of the slope. Everything that's estimated will get a t-stat. So we'll be able to see if these slopes that are estimated, we'll be able to see the economic magnitude, and we'll also be able to see the statistical significance of those slopes as well. Here's the formula for prediction. Similar to when we just did one mean, we have s squared into 1 plus 1 upon n, and now there's an extra factor that depends on the regression term. X sub f is the future level of X that we want to make our prediction at, and so we need to see how far away is X sub f away from X bar. Remember that this term here will be equal to 0 if the future X is equal to X bar. And again, that makes sense that the prediction bounds will be smallest when you're trying to predict at the total average level of all of the X's. And of course, the output variable there will be the average Y. And again, the R command is the predicts.lm command to get that. So here's sort of a quick little summary of all of the facts of how the prediction errors change as you're building these models. The larger the S, or the larger the errors, of course, the larger the prediction bands. a small n or not enough data, you can have large prediction bands. A small s sub x, not enough spread. So if I go back, I'm essentially looking at this formula here. If s sub x is small, the prediction bands will be wide. And then if I'm predicting a long way away from the average, if I'm trying to predict in the extremes, I get a large prediction error. So interesting to see under what conditions that prediction bounds will be high. And just from a lot of practical experience, I tend to look at the S values, and I really don't spend much time looking at R squareds and regressions. Remember that correlation is not equal to the slope, so I'm much more interested in finding what are the beta hats for all of my X variables, and I'm also much more interested in checking for diagnostics. Are my modeling assumptions actually true? Things like T ratios and P values don't really make too much sense if my assumptions aren't true. Okay, so there's what I want to say about prediction. Let's do a very simple example. So let's go back to our Google stock returns and make a slightly more complicated model. And we want to try and figure out how does Google stock move up and down as the S&P index of stocks, the top 500 stocks in the US, moves up and down. So is there a relationship? And as I said before, the nice thing about R is lots of people have written libraries and packages. So in the QuantMod package, you can go to Yahoo Finance and you can download daily data of Google and put it into Y. Two useful commands, a head and tail, just to show you what the beginning and end of the data set looks like. Now here's a classic regression. It's called the CAPM regression, capital asset pricing model regression, and really it's the first baby regression you could run in finance. Let's look at the returns on Google and run a regression of the returns on the S&P. And really what we're looking for is we want to see how sensitive or a hypothesis we would be interested in H0 is Google related to the market. And of course the answer is going to be yes. If beta is equal to 1, it will move up and down in locksync with the market. Now, does Google outperform, so this is the beta that we want to look at, does Google outperform the market in a consistent fashion? That's the alpha. And if the market was efficient and more knowledgeable, you would like to think that the alpha is pretty close to 0. A stock shouldn't be able to consistently, day in, day out, even if it's by a small number, beat the overall index. Oh, and then remember that there's still an error term. Sometimes the finance guys will call that the idiosyncratic risk. And that error term will have its own standard deviation sigma, which will also estimate S by the residual standard error. Oh, and then we could do A/B testing, for example. We don't just have to look at Google. We could look at another company, say, for example, NVIDIA. Google has TPU chips. NVIDIA has GPU chips. So they're not in the same business, but they're both AI companies. And we could start to ask questions of, how do you compare Google with NVIDIA, say? Again, the first thing to do is just to plot historically the data, right? What do the returns look like for that little period you're looking at? And remember that all regression is doing is, with one Y and one X, you can do it by hand. It's just fitting the optimum least squares regression line through that data. Now, of course, with multiple X variables, that's going to be a much more complicated problem. And again, you can already see that there are going to be outliers. Remember, outliers are measured by the residuals or standardized residuals from the line. Anything with a standardized residual bigger than 3 will be seen as an outlier. And you can just see that the variance on a day-to-day basis of Google, because of idiosyncratic risk, is bigger than that of the index. Okay, but as a general rule, there's a nice linear relationship between Google and S&P, and that's finding the beta. And again, when the S&P is 0, we'll go up to the line and we'll see what would happen on average to Google if the S&P on average is 0. And just one other further comment. This is just the beginning of what's known as factor modeling finance. Clearly, I can nearly already think of a whole bunch of other X variables I want to add in. For example, Google is a technology stock. Maybe I want to add in the NASDAQ index. There are clearly days when Google has earnings. Maybe this was a negative earnings day. So I might want to add in dummy variables or indicator variables of earnings days as well. And I can keep on going. Large cap stock, small cap stock, growth stock, value stock. So I can build up what's known as a multi-factor regression model. Okay. Now, what would that look like in R? What output do I get? So let's just quickly look at that. Really, so as I said before, the summary command is my favorite command. After you've done model equals linear model, run a regression of Google on S&P, you look at summary model, and essentially what I'm looking forward to getting is what my estimates are. Now again, my alpha is real small, and my beta is about 92%. The t-value, the beta is measured very accurately. Remember, any t-ratio bigger than 1.96 is statistically significant. Corresponding to an incredibly large t-ratio, I have an incredibly small p-ratio. Now, it's much harder to measure the intercept. So at the 95% level, I haven't gotten up to my significance level. But 0.004, remember to multiply by 252 to get to a yearly basis. That means Google outperforms in a year on average about 10%. 0.004 times 250 or 252. So there's a economic significance versus a statistical significance. And again, without more data, we're not going to measure accurately what that alpha is. So in this case here, it's about an extra 10% a year. And as I said before, if the market was efficient in theory, we shouldn't be able to find a significant alpha. So there's a statistical tool, a technique. We have enough computing power to run that regression on every single possible stock, and so we could go mine the Yahoo Finance data set for stocks that have significant alphas that are outperforming the market. So a useful tool. Okay, here's another finance example just to make the point. John Maynard Keynes was a very famous English economist. I remember he wrote a book about probability, a treatise of probability. He wrote a lot about economics. He had his theory of labor and economics and government spending. What people maybe don't know about him was that he also invested Cambridge University's or King's College endowment. So he was given the task of deciding where to invest it. And I thought this data set would amuse you. Remember, the stock market crashed in 1929, but the crash happened after a dramatic increase in stocks. So believe it or not, he actually made money in 1929, even including the crash. But where he lost money was in 1930 and 1931. He lost minus 32%, 1/3 of all of the college's money. Then he lost another 24%, and it was only until the mid-30s, the Depression years, when he actually was able to figure out his investing style and made an incredible sum of money. What would that look like on a graph? Well, he's incredibly volatile. So the red line is if you just left your money sitting in cash, in T-bills. He had rather crazy, as I've said, many large losses, but also big recoveries. And again, if we ran the regression, clearly his beta is going to be much bigger than 1. I think he has a beta of like about 1.7. So for every 10% move in the index, he'd have a corresponding 17% move. Okay, so we're doing the theory of linear regression. We've covered least squares. Now we've got a couple more things to cover: outliers and influential points. So I've already talked a little bit about it, but the residuals, the EIs, let you define outliers. and more specifically the standardized residuals. So EI divided by the standard error puts everything on a normal 0-1 scale. So, a little bit more than 95% of the time, the residuals will lie between -2 and 2. And as I think I've said before, any observation that misses our fitted regression line by more than 3 standard deviations is going to be deemed an extreme outlier. Now, that's not saying you should delete those points, but you should maybe look more carefully at them and see if there's any missing X variables that would maybe predict them, etc., etc. And sometimes they're interesting cases just to discuss. One of the interesting things about outliers is typically if you delete them from the data set, the actual regression model doesn't change much. The beta hats, they're typically extreme in the Y space, and being extreme in the Y space generally doesn't affect the beta hats and the regression line. Now, that's as opposed to something called influential points, which are far more important to find. Influential points are essentially points that are extreme in the X space. And why are they so important? Well, they affect the magnitude of the beta hats. And there's something called Cook's distance. Dennis Cook is a statistician in Minnesota, and he has a measure. If Cook's distance, you'll see in a minute, we'll cut it up into 3 ranges: 0 to a half to 1, and above 1. If Cook's distance is above 1, we'll typically delete those data points from the data set, and we'll rerun the regression to see how much our beta hats change. Okay, so influential points, in some sense, much more important to find than outliers, and sometimes you'll end up reporting 2 regression models. The regression model with all the data, and then the regression models taking influential data points out to show you how your conclusions change. So here's a formal definition of Cook's distance. It depends on the standardized residuals R sub I, and it depends on something called the leverage factor. And the leverage factor helps us calculate what the variance is of those residuals. And again, if you use plot Cook's distance in R, you'll find a time series or a by case index plot of Cook's distance. If you define a new data set as data minus I, it'll delete the ith row, and the idea is you're looking to see whether the beta hats change. So important thing to look at. As I said before, there's 3 regions. You'll see there'll be a 4-in-1 residual plot. So you'll see the 3 regions. As I said, anything with a Cook's distance bigger than 1 will generally be a warning sign that you want to take a look at it, take it out and see whether things change. So, just as a matter of good practice, I generally delete the point with the highest Cook distance just to check it doesn't affect my observations. So now, not deleting outliers, just explaining outliers, trying to figure out if I'm missing X variables. Now, all of this is done before I allow myself to look at summary model, before I allow myself to interpret my model, before I allow myself to look at t-ratios, and before I allow myself to do predictions. So the influential point stuff is part of your diagnostics paradigm that you should be done before you do any formal statistical methods. Okay, so in summary, I have a 5-point regression strategy. So let's go through it. First of all, input, try and plot data. But of course, in high dimensions, that's much harder than it looks. But you can look at bivariate plots and maybe correlation plots if you want. But typically, the high dimensional structure can easily be masked. Then, as I said, one of the key commands in regression is that linear model command. And typically over here, I'll have multiple X's. I'll be running a multiple regression. Now, after I've created that object, I'll look at plot model, and you'll see it's called the 4-in-1 diagnostic plot. You'll see fitted values against standard residuals. You'll see what's known as a quantile plot for the outliers or residuals, and you'll find outliers and Cook's D. So you'll see a 4-in-1 plot. Sometimes I'll do transformations of my variables. I'm coming to that at the end of this week. So if my assumptions don't look true, that'll motivate me to look at transformations. When I'm happy with all my diagnostics, I'll do the summary model command, I'll look at the regression beta hats, and I'll do some form of variable selection. And what do I mean by that? Well, in a multiple regression, I like to use the threshold 1.5. I think 1.95 is a bit too stringent. It's hard to measure these marginal effects unless you have a lot of data. So my rule over years of experience would be to look at any variable with a t-ratio less than 0.5. I'm suspecting that its beta is equal to 0, and I would delete that variable from my regression and rerun. And essentially, I'm doing that to get better beta hats of my significant variables. And all this is said with the caveat of economic significance and just pure common sense. If you're worried about throwing a variable out, the simple rule is just to leave it back in, and don't 100% go formally by these formal statistical rules. There's many other things like forward selection, backwards elimination, which are not my favorites. I prefer to, when I do my variable selection, I prefer to group together all variables with t-ratios less than 1.5 and to delete them all in a batch. And doing too much of that can lead to a bunch of biases. And of course, the whole goal at the end of the day, just like our house price Zillow examples, is to come up with predictions. I've got a sequence of new x's. What's my predicted new y? Here's a summary of the key R commands that you would need to know: correlation, linear model. GLM stands for logistic regression or generalized linear model. Model regressed on p variables. And the diagnostic commands are all in the plot model command, plot Cox distance, and then if you actually want to look at the outliers, the RStudent command. So that gives you a pretty good summary of the R commands that you need. Okay, and again, very similar to that basic house price example we did. After you've done the summary model command, you create a new data set, a new data frame, where you list out the x's that correspond to your new x variables. Be a little bit careful if you transform the variables. You're inputting the transformed values of those new variables, and then you just use the predict.lm command on that new data frame with the model that you've estimated. And your data frame variables have to match up with the variables that you've left in your regression. And as I said, you have to be careful that you incorporate your transformations as well. And the whole goal is that I'll get a prediction at a whole bunch of new inputs, and I'll also get prediction bands for those as well. For your diagnostics, so let me just be a little bit more specific about what you get in the plot model command. So this is my 4-in-1 plot model command. You get residuals versus fitted values. You're really looking for just a random pattern distributed about 0, so a straight line about 0. There shouldn't really be any extra patterns left over in the residuals against the fitted values. If there are, that's a sign of nonlinearity in your data, and you might want to think of, if that doesn't look, you might want to think of transformations. And that's transformations of y and or x. The transformation on y will clearly have greater effect on straightening things out. We won't talk much about the scale location plot. Essentially, it's for checking changing variance or heteroscedastic errors. I like the normal quantile plot. What's a quantile plot? It's looking at the 10%, 20%, 30%. It's looking at percentiles of the distribution. So it's looking at the empirical percentiles of the standardized residuals against what you would have expected from what is true. And of course, remember, our assumption is that our errors are normally distributed with mean zero variance sigma squared. So standardized would be normal 0, 1. So again, you're looking for a straight line. It's a bit of a finer test than just looking at a histogram. So look at the normal QQ plot. Any kind of deviation from a straight line, again, transformations. And typically you get to see the outliers and the extremes. You get to see which which points are missing on the left side or on the right side. And then finally, Cook's D will try and find influential points. In R, you simply use the plot model command, and you do all of this before your summary model command. So just to remind you that none of the t-ratios or p-values or interpretation of the models clearly don't hold true if your assumptions don't hold true. So if you don't have a linear line, you shouldn't be using regression. Oh, and I should also say that R is also running linear systems on transformed equations. So you'll see in a minute that linear regression is a lot more powerful than just simple straight lines between y and x. Okay, let me do a famous old example that just illustrates influential data points, and then I'll do an example that'll illustrate outliers for us. And then next time we'll look at multiple regression, and we'll look at some transformations as well. So here's a famous example: lung cancer versus cigarette consumption. So cigarette consumption in the 1930s versus lung cancer deaths per million in the 1950s. And I guess the two countries of interest are the US and given I'm from England, Great Britain. And I find this an interesting data set that in the 1930s there was a lot of cigarette consumption in the US, but 20 years later they really didn't pay the price of many deaths from lung cancer, whereas the British did their very best to consume as much as the US in terms of cigarette consumption, but dearly paid for it in terms of lung cancer deaths in the 1950s. And again, we're just looking at regression relationships. We're not trying to get to the causation level of why that's true. I'll never forget, but one of my students one year said, this is the causal effect is quite simple to figure out. Essentially, in the 1930s, all of the fit, strong people left Great Britain to come to the US. So that's why they didn't die 20 years later. I just want to use it as an example to show influential points. Clearly, the US is going to be an influential point. So if I look at the regression line, the optimum beta hat with the US in, that's the red dotted line. If I take the US out, the effect for the European and Scandinavian countries becomes much bigger. I get the dotted green line. And again, that's something that Cook's distance would diagnose for us. If I look at our 4-in-1 regression plot, residuals against fitted values, it's supposed to be a straight line. There's our point that's missing. So the US is sitting down here. Way fewer deaths than the model would have predicted. Scale location is showing that the variance is not heteroscedastic. Again, our US outlier is there on the normal QQ plot. I think this is Finland up here. Slightly more deaths than you would have expected. And then remember Cook's distance. So let's have a go at this one. You get what's known as isocontours of Cook's distance. So anything outside this dotted line here, any point out here, has a Cook's distance bigger than 1, right? So again, the US is a prime example. Cook's distance bigger than 1, take it out, rerun, and refine the beta hats. Up here, actually let me just check. Number 11 was actually Great Britain. So there's Great Britain up here. More deaths than you would have should have happened, and everybody else is in the range from 0 to 0.5, so not influential. So one influential point, which is also an outlier, and if I rerun the regression, I can see the difference in effect. Again, if I do model 2 and keep on doing it, again I get a different plot. Partly why I tend to do these things in one go. Something else will turn up influential if you're not careful. And again, coefficient model, you can find the key thing you want to know is what's that regression beta hat. Okay, so final example, I want to look at transformations. So we have a basic assumption of linearity. And what happens if that doesn't hold true? So a simple approach is just to transform the variables and then rerun the regression on the transformed variables. If everything is fine, and by that I mean if my diagnostics, my 4-in-1 plot looks fine, if it holds on the transform scale, then I'll just transform back to the original nonlinear scale. So linear regression is really quite a powerful tool because of this idea that I can transform ahead of time and I can essentially fit a set of nonlinear models. And the two that we'll look at are the two most common ones, particularly the power one. Let's look at how do you estimate power relationships in R, and then we'll also look to see how you estimate an exponential relationship. So by a power relationship, I mean a multiplicative model. So I mean a model that looks something like this. Y is equal to some big constant, capital A, x to a power. And if I thought about drawing what these curves looked like, there's my x and there's my y. A linear straight line, beta equals 1, would look something like this. A quadratic, beta equals 2 would look something like this. And a beta equals a half, the square root function would look something like that. So there's a whole bunch of different shapes that I can get, and then of course random points dotted around that as well from our regression error. Just for notational convenience, let big A be equal to e to the little a, and then I can think about taking logs. So let's think about this model here and try and match it up with what we would get up top. So here's our usual regression model. This is just a simple linear regression that we can fit in R with the LM command. Now, if I look at this top equation and take logs, I get log y is log a plus log x to the b. And the b pops down out front, and I've got to match up with my model above. And so in matching up, I realize that b is equal to beta 1, and I realize that log a is equal to beta 0. So rather nicely, if I run a regression that looks like this, I can essentially go back and estimate my power relationship. What would that look like in R? I'm running a model of log y on log x. And there's a nice interpretation of the slope of that log-log regression. It's something called an elasticity. And it means that it's on a scale where if you think of a percentage change in x, I get to estimate what's the percentage change in y. So a 1% change in x would lead to a beta 1% change in y. So there's lots of variables like size or weather or other such variables like that where you're more interested in, okay, what happens if climate changes by 2%? What are the implications for other variables from that? So log-log model is very useful. Let's do exactly the same thing for the exponential model. So instead of y equals big A x to the b, y equals big A e to the bx, and again my a is equal to e to the a. I'm going to run a regression of log y on x, not log y on log x, and again I want to match these things up, and essentially my beta 1 will be equal to b, and my beta 0 will be equal to log a. So I run a regression of log y on x to figure out an exponential relationship. Now, once you get to learn about logs, you get addicted to them, and sometimes you look at a data set and you just start by logging all the variables to begin with because you realize you'll get much better fits to your data. But a little bit of a caveat, not all variables can be logged. So for example, you need to have positive variables. You can't take log of 0. And actually another nice thing that log does is if I have a skewed variable, it tends to do very well. So by skewed, I mean a small number of big extremes. Once I take logs, it will cure that, and when I run my regression on a log-log scale, it'll look much more linear. Another class of variables, sometimes they're called one-hot encodings. I like to call them indicator or dummy variables. So X is either switched on or switched off, two different groups. Clearly those variables can't be logged. And again, counting variables you generally leave alone. So if you're measuring age in years, as a general rule, you wouldn't take logs. You'd leave those alone. Okay, so there's two transformation models that we have. One is our log-log model. That'll correspond to a power, and our other is just log x on x. That will correspond to an exponential. Okay, let me do my mammals data set. One of my favorite movie sketches in a movie called Phenomenon with John Travolta is called Specifics Bob, and he lists out a whole bunch of mammals, and he also makes it very clear, like in a Bayesian fashion, when if you're asking someone a question and you want an answer, you have to be very specific about what the answer is. So Google Specifics Bob, and you can see an interesting sketch with John Travolta listing a whole bunch of mammals in alphabetical order. So I took a data set of mammals. There's my head of the data set, the beginning, and there's my tail. And the whole idea was it's not a causation model. It's just a predictive model in some sense. Can I relate brain weight to body weight? And what's interesting about this data set is if I plot my data, I think this is the blue whale and this is the African elephant. So the blue whale has a brain that's way, way bigger than us poor humans, and I think we're somewhere down here. So blue whales and elephants have much larger brains than us, but regression really doesn't fit the data because I've got these incredible extremes. So if I ran the regression, look at the residuals, I want it to be a random plot about 0. It doesn't look like that. It gets biased by those two incredibly large data points. So again, if I looked at my plot model, my 4-in-1 plot, Cook's distance would tell me something crazy is happening, and the QQ plot would also tell me something crazy is happening as well. So on a linear scale, it doesn't make any sense. Now, here's the beauty of taking logs. So let's just see logs in practice. So let's put everything on a log scale, log. And you see the two extreme body weights and brain weights get brought back in. The scale changes dramatically on both variables. And again, now I've really got a perfect straight line between my brain weight and body weight. So now I'm very happy. When I look at my residual plot, it's basically a random plot about 0 with constant variance. Again, that's showing that my assumptions about the error distributions, about the residuals, about the line holds true. Now, another reason for doing this was I wanted to try and assess, the world's smartest mammal. So what mammal has the largest positive standardized residual? And I guess by the same token, we could also find the world's stupidest mammal, I guess, if you want to do that. And I guess I was hoping that we'd find that mankind is the world's smartest mammal. Let's see what happens. Well, first of all, diagnostic plots. There's a little bit of art to these things. Nothing will ever be absolutely perfect. But there's no Cook's distance bigger than 1. There's my 0.5 range. So this one here is good. This one here is pretty much a straight line. It's okay. Again, pretty much a straight line. Maybe there's still a couple of outliers left over, and hopefully this one is our world's smartest mammal. So hopefully we are a little bit of an outlier relative to the line. There's a regression equation. As I said, I'm not trying to find a causal effect. There's a correlation between the variables. Remember what I said before, that you're really just trying to find beta hats. You're not really, correlations are sort of a secondary thing. And again, remember that this is a power. If I transform back to the original scale, this is a power relationship between my variables. Now let's go to our outliers. What has the largest outliers? And we have two candidates. There's mankind. We're currently in second place. And if you believe my regression, the world's smartest mammal is a chinchilla. So I guess I'm trying to say that, or trying to prove that the chinchilla is an animal, a master race of supreme intelligence. I think the fur of a chinchilla is used to make fur coats. So he has the extreme outlier. Actually, it's a sad ending to this little regression. I went back to check my data, and I'd actually made a mistake. the chinchilla goes from one of the smartest animals to one of the not so smartest animals. If we look at my little regression, mankind comes out with the largest positive residual. And again, just to recap, you'll see me do the log-log transformation is very popular in not just linear regression, but also in multiple regression as well. So it's definitely something you'll see in future lectures. Okay, just a quick glossary of symbols: intercepts, slopes, errors, residual standard error, standardized residuals, leverage. Make sure you know what they are. And again, we covered a lot of material. The chapter in AIQ to look at is the Henrietta Leavitt chapter. Zillow is one of the leading companies looking at data analytics and providing useful information about house prices with its Z estimate and maps of previous sales, etc., and how different parts of houses are valued. We covered the theory of simple linear regression. We talked a little bit about trees. Zillow uses a lot of random forests and tree models to make predictions. So we talked about predictions. We looked at Gauss's least squares principle. We looked at a Google S&P example. We looked at an influential outliers example with cancer and smoking. And then we looked at a data transformation. We looked at our log-log model. Okay, thank you for listening.